think it's already going.
Yeah, already recording.
Ah, it's done already. Okay,
Yeah.
very good. Okay, so good afternoon, ladies and gentlemen, dear colleagues. Welcome to our second interactive webinar, which was actually supposed to be the first one, but then due to force majeure, it was postponed, so now it became the second, but this was the original plan. As you may know, or maybe you haven't heard yet, the interactive webinar series aims to combine the knowledge of experienced researchers with the drive and passion of early stage researchers and the extremely important contribution of our technicians. One of the key goals is to share our experiences, learn from the challenges that we are facing when performing physical modeling experiments. The webinar will be interactive, as you will see, and we will try to promote active involvement of online participants. Please, everybody who is not a speaker, please mute so that we don't have any disturbances. So recognizing that we can learn more from failures, we have asked the speakers to share problems they faced and how they solved them. So let's see what problems this team faced during these very interesting experiments. I believe that this is better than just going directly to the success story because we can learn more. The webinars are fully open to attend online and are also recorded, so it is recorded at the moment, and will be posted on the TC104 website for everybody who is interested to be able to watch. I would like to welcome our speakers. So we have, as you can see in my slide, Professor Sam Stanier from University of Cambridge, Christian Peter from the Schofield Center, also University of Cambridge, and Dr. Elena Dodaro from University of Bologna, and Mario Marcolongo, also from University of Bologna. The talk is a result of a collaboration between Cambridge and Bologna, which was part of a GeoLab project. And the title is Centrifuge Modeling Techniques for Investigating River Embankments Behavior Under Steady State and Transient Seepage Conditions. So I'm very much looking forward to see the very interesting processes, problems, solutions, and conclusions. The floor is yours.
Thank you very much, Yanis.
Thank you very much. So I will share the screen. And first of all, I would like to sincerely thank Professor Anastasopoulos for this great initiative and all the present for attending the seminar. So I will share the screen and leave the floor to Professor Stanier, which will introduce the presentation.
Okay, thank you very much, Elena. So my part in this, in the initial stages, is going to be relatively brief. I'm going to set the scene for the project and give you an overview of what we're going to talk to you about today and signpost where we're going to stop and try and be interactive to meet Yanis's brief to make this a back and forth between us and the audience. So you've already been introduced to the speakers, so I won't dwell on that. You've obviously also been told what we're going to talk about. So we'll move on to the content slide and I'll break down our talk.
Sam, we cannot see the slides yet.
Oh, okay. I can see it for some reason. Let me know when everybody can see it.
I cannot see it yet.
Okay, I can try to reshare the screen again.
It says that you have paused screen sharing.
Okay, I will try to share the screen again.
Okay.
Can you see them now?
Yes.
Perfect.
Perfect.
Okay.
Okay, so first of all, we're going to have a few minutes of me. I'm going to introduce to you the GeoLab Horizon 2020 project and talk a little bit about how this project that we're talking about today came about. I'll also touch on where we've performed the experiments, which is the Schofield Centre here in Cambridge. Then Eleanor will come on and talk in more depth about the proposal that she ultimately wrote. So the origins of the proposal, what the problem and motivation statement is, etc. And then start thinking a little bit about how we were going to try and model this problem in the centrifuge. Then Eleanor and Marco are going to come in and talk a little bit about the experimental setup, so what we had to develop in terms of apparatus. We'll pause a little bit and think about the difficulties with a cross-continental collaboration, where there are limited amounts of time where all parties are in the same place at the same time. And that's where Christian is also going to come in and talk a little bit about the host perspective from a technical standpoint. And then finally, at the end of the session, myself and Eleanor will wrap up with some of the main conclusions of what we think we found out from these experiments. So moving on.
Yes, I'm trying. Okay. Okay, here we
So
are.
first of all, why GeoLab? What is GeoLab? So GeoLab is a consortium of partners across Europe that each have a piece of physical infrastructure that can be used for physical modeling of geotechnical problems. And the focus of GeoLab is on critical infrastructure that's threatened by climate change, extreme weather, geohazards, aging, intensified change usage, all of these kinds of things. And the idea of GeoLab was that it was to be a network across which the whole of Europe could have access to these disparate and different facilities that each had different capabilities for performing physical model tests. So the idea of GeoLab was to bring those facilities together. We had 3 separate competitions for funding for non-participants of GeoLab to apply for funding, and they were each targeting one of the facilities that we host across Europe, which you can see on the next slide. So GeoLab, if you think about it in terms of the infrastructure it provides, it's just a kind of one-stop shop going from small-scale laboratory testing, which we focused on mainly in Slovenia, but I've put a plus there because quite a lot of the other facilities have aspects of laboratory testing that were available to participants too. We have a large number of centrifuge, which is what we might refer to as our mid-scale modeling approach. So small-scale models, but with stress similitude accounted for in a centrifuge, and there were 7 of those dotted around the various facilities and various forms: beam centrifuge, drum centrifuge. We've even had one be commissioned during the duration of the GeoLab project itself in Zurich. Then there are what we call large scale, and there are 3 such facilities looking at full scale testing in the lab, or close to full scale. And then finally, we had 1 field testing suite in Norway. So altogether, you can see you can cross the scales with the infrastructure that's available for physical modeling at these different institutes. And today's project is going to talk about a project conducted at the University of Cambridge. So moving on to the next slide. As I've already said, there were 3 rounds of peer-reviewed project calls, and the calls were on, firstly, experiments that provide or prove innovative solutions to enhance the resilience of the critical infrastructure in Europe. The second call was on experiments to study the pressure on critical infrastructure, particularly impacts of climate change, aging, increased usage, etc. And then the third call was about doing experiments that would complement numerical work. So trying to validate numerical techniques with experimental data. And so across GeoLab over the last 5 years, there were 24 projects awarded that involved 137 separate individuals at 74 institutions and companies. And so what we're going to talk about today is just one of those projects. We move on to the next slide. So the focus of today's talk is the Res Fluctis project. It's assessing river embankment stability due to floods, and particularly focusing on unsaturated conditions in the embankment. And so the aims of the project were to look at the hydromechanical behavior, but in particular to focus on the effects of the partial saturation in the embankment itself, which is not accounted for in design and can have a significant impact on stability. And so what we were really interested in was the failure mechanisms during the onset of slippage of the embankment. And so with that, we'll move on to the next speaker, and Eleanor is going to talk you through the context and project aims.
Okay, thank you very much, Sam, for the introduction, and good afternoon to everyone. So as Sam has already said, I will move quickly to the motivation that lead to GeoLab Res Fluctis project. So due to the major impact of climate change and the spatial expansion of urbanized areas, extreme geohazard events such as earthquakes, volcanic eruption, floods, and storm have become more frequent and of greater magnitude and frequencies. So flood and storms dominated across the last 2 decades, with a number of occurrences much higher than the other events. So if we look at the map on the right side, we can see the total number of river flood events that occurred in the last century, grouped by country. We can see that from a geographical point of view, the events were quite unevenly distributed, with a concentration on the Western Europe and Southern Europe. And Italy was one of the most interested by this event, causing, of course, casualties, damages, and huge economic losses. So the situation in Italy is very dramatic, because we can see that hydrogeological instability is a topical issue. And if we look at the hydraulic hazard map of Italy, considering the medium probability scenario of flood-prone areas, we can see that the region of the center and the north are quite interested for this kind of problem. And in particular, if we look at the situation in the Emilia-Romagna region, we can see that this concentration is ascribable to the presence of the main hydrographic Po River catchment and to the dense network of tributaries and secondary artificial drainage channels. If we talk about Emilia-Romagna, we cannot forget to mention the devastating effect of the flood events occurred in May 2023, which interested more than 100 rivers, and we observed more than 66 main collapses on 16 rivers. So the situation was really devastating. Here I reported some pictures and a video from the cited events, and from a subsequent one that occurred in September 2024, exactly in the same areas. So with the red line, you can see the original shape of the embankment section, and with the dashed line, I tried to highlight a typical sliding surface that occurred during the event. All these embankments present some typical characteristics. So they have a height above the ground level between 5 and 10 meters, an inclination of the slopes up to 35, but sometimes in critical section it can reach 50 degrees. The material constituting the embankment is usually an heterogeneous mixture of sands and silts, while the foundation is characterized by deposit of fine-grained material. So if we look at typical failure mechanism for this kind of earth structures, we can subdivide them into two big families. So the hydraulic collapses and the structural collapses. From our point of view, the structural collapses are much more interesting, because hydraulic collapses are related only to a capacity problem related to the impoundment of the seabed. While on the structural collapses, we can identify three main families, all related to the action of the river. So we can identify external erosion, which usually affects the inner side of the embankment. Then slopes instability, which will be the focus of our project, and we will see some examples of this kind of instability happened in the centrifuge. And then internal erosion, which is a huge family of mechanisms related, for example, to uplift and piping. But what does it mean assessing the safety and the stability conditions of a river embankment? So the stability of these particular structures are intimately linked to the seepage characteristics. So we need to start from the identification of the most critical hydraulic loading condition, and after that, so after defining the seepage characteristics, we can determine the factor of safety with respect to a certain failure mechanism. So the factor of safety is generically defined as a ratio between the resisting capacity in terms of shear strength mobilized and shear strength, and divided by the applied load. So in the current engineering practice, the regulation that governs the design and assessment of geotechnical engineering work, among which are, of course, river embankments, are the Eurocode 7 and the Italian Building Code of 2018. These kind of regulations are not so specifically are not regarding the hydromechanical behavior of river embankments. So they usually made some simplifying assumption. So, for example, they prescribe to work and consider steady-state seepage conditions in equilibrium with the expected maximum water level, and the effect of the variation of degree of saturation, so the effect of partial saturation, especially on the shear strength of the soil, are often disregarded. This leads to over-conservative stability results, which is not usually a big issue, so cannot consider a proper drawback. But more importantly, we don't know the effective safety margins towards potential failure mechanism. And this is a very bad news, because it's not possible to decide an intervention priority. Okay, so in the subsequent two slides, I reported the results of two numerical finite element analysis conducted both in transient seepage conditions and in steady-state seepage conditions, to highlight the implication of considering these two different hypotheses. And the effect of partial saturation is taken into account in the first one, while not in the second. So I considered a typical geometry and the characteristic of a section of a tributary of the Po embankment, of the Po River, sorry, and I performed a calculation by considering a realistic a real hydrograph recorded during a high water event that occurred on the 6th of December 2020. So we can clearly see that if we start from an initial conditions that consider partial saturation, even the main hydrometric peak that was recorded during the flood event is not able to saturate the core of the embankment. While if we consider a steady-state seepage conditions in equilibrium with the maximum water level, of course, all this part is saturated. So if we compare the factor of safety obtained in the first case in equilibrium with this level, and again, we compute the same factor with the simplified assumption, we can say that in the first case, the river embankment has a stable section. So the factor of safety results 1.71, well above the unit. While in the second case, the factor of safety is 0.89. So we are in a potential failure conditions. So what we can learn from these simply analysis, that of course, considering transient seepage is crucial in our design and assessment of these structures, as well as the role of partial saturation. Okay, so this will lead me to the first interactive part of this webinar. So here we have the opportunity to share experiences. So I would ask to the audience how are river embankments designed and assessed in your region, if you have guidelines specifically related to this kind of structures, and if you consider this aspect in the design and assessment.
Thank you, Elena.
Thank you.
It's nice that you also pose the question.
Yes.
But let's see what questions come from the audience.
Yeah, of course.
So if you would like to ask a question, please raise your hand or just activate your sound and come forward.
Yeah.
Maybe ask one
Okay.
question just to start. You mentioned partial saturation.
Yes.
So which part is partially saturated and which part is not, or is it all of it?
Okay, I will reshare the slides. So, for example, if we look at the initial conditions of this analysis, we can see that the part under the phreatic surface is considered saturated, while this part right above the phreatic surface is called capillary fringe. And due to the capillary rise of water between the void of soil, this part is not fully saturated and is not dry. So it has a specific hydromechanical behavior that is influenced by the presence of three phases. So the soil, the air, and the water. So all this part has a special behavior, let's say, okay?
I suppose this will come later on when you describe the experiments. But
Yeah.
now the question that comes to mind is, how big is this partially saturated zone in the prototype?
Well, this is very difficult to estimate, and this is the reason why we need to investigate this kind of contribution, because even if in the lab, in the laboratory, we have the possibility to install instrumentation and properly control all the boundary conditions, on site, this kind of analysis is more difficult. So one of the key issue on site is estimate the initial condition when we have, for example, a high water event. So we can use, of course, pore pressure transducers, tensiometers, but the cost of the installation is quite high and it's not very easy to have a proper monitoring layout distributed along kilometers of these earth structures. So you have to imagine that this is very difficult to estimate.
I was going in the direction of understanding how this can scale. So let's say your capillary height is, I don't know, a few centimeters in the prototype. Yeah. What happens when you scale it down in the centrifuge?
Well, this is one of the frontier to understand properly the scaling laws between model in partially saturated conditions and prototype. But for a rough estimation, you can consider the same geometric laws just to start.
I see Jan raising a hand.
Yes?
Yeah. Just two things after you mentioned your comment, Yanis. First of all, about the scaling. There was a conference in La Baule about 25 years ago, I guess. I'm getting very old. And there, that was the European project dealing with scaling laws when it's about unsaturated behavior. The second comment I would like to make is that we had an experiment of a small scale, big scale dam. So we built a dam about 4 meters high and filled it on one side, left it like that for about 3 years. And it took about 2 years to fully saturate. So we found a saturated zones on the top where you assume your seepage line and on the bottom, but we had a bulk of material unsaturated in the middle. And that I found very interesting. I want to look further into that, why that is. But we have the physical data of this, and we know we recorded the filling height, we recorded the flood event, or the water content or the water height, and we had pore pressure transducers inside the dam. So we had recordings wherever in the dam we have a saturated zone and where we have unsaturated zones. So it's a very interesting topic.
I totally agree.
Thank you, Jan. I see Sid is raising a hand.
Yeah, hi everyone. Thank you for the great presentation. you have a great point about initial conditions and having the right instrumentation for capturing the initial condition. Absolutely. But I think we should also make sure that you can capture variation in saturation. So the behavior under variable saturation during the test, both experimentally and numerically. So the numerical model should also be able to capture that change in degree of saturation over the test. And another thing I wanted to mention, we are struggling with the same concepts at University of Colorado with flood and earthquake and use of viscous fluid. Yeah, this is an interesting area with partially saturated soils and variations in saturation in dynamic events as well. That's not well resolved yet.
Yeah. Okay. Thank you, Shide, for your intervention. So I will start with the first observation.
Hang on. I think Adam Bazine might have something to say, and I suspect it might be relevant.
Okay, of course.
Just given your location, Adam.
Location at home in the Netherlands. So, but I was wondering about the calculation you showed, because I see, if I understand it right, that you have very high suction pressures of minus 60 kPa.
Yes.
And then you get a safe embankment. But in reality, of course, the suction pressure for normal, depending on the material, can be much lower, and then probably also the safety factor will be much lower. And so probably this is a bit extreme what you had on difference in safety factor between time dependent and not time dependent.
Yes. So if I can add something to this analysis. So I went pretty fast, but you can find all the detailed calculation into the article that I reported at the bottom of the slide, which has been recently published on the Journal of Geotechnical and Geoenvironmental Engineering. So regarding your specific question, this particular distribution was obtained at the end of the in-flight consolidation of a centrifuge test that was used to calibrate this predictive numerical tool. So I performed it was a group, not me directly, but we performed a series of centrifuge tests that was inspired to river embankment of the tributaries of Po River, which were characterized by peculiar hydraulic and mechanical characteristics. So at the end of the in-flight, we were keeping the water table at the ground level, and then we observed through miniaturized tensiometers, which was the distribution of pore water pressure and suctions. So this was the initial conditions for our analysis. Of course, this can change a lot, considering different seasonal changing and daily variations. For example, in this analysis, we didn't consider any influence related to precipitations, and we we disregarded the control of climatic boundary conditions in the centrifuge. So all that happened was related to the natural drying during a spring test in the lab.
Yeah, but you found really the minus 60 kPa that is also in tensiometers.
Yes, we measured this value at the top of the crest. So close to the crest, there was this very thin layer in which we reached minus 60 kPa, but the core was around minus 20. Yeah. It's an hypothesis, as I said.
You say hypothesis, or that is really measured? That's a different thing.
Yes, the distribution was obtained with by putting the exact measurement obtained at the end of the in-flight consolidation, because we had different tensiometers inside the embankment at different depths, and it was possible to reconstruct the distribution. So with this contour, okay. Thank you for your question.
Thank you. I see we have one more question by Lane.
Yes, please.
Hi, yeah, I was just wondering if you considered how the cyclic wetting and drying changed the strength profile of material.
Yes, we did.
Yep.
And I invite you to read the paper, but you will see something very interesting towards the end of this presentation, because we did this test during the GeoLab Res Fluctis project. So you will see how the suction and pore water pressure distribution will change accordingly to the water level change and to the retention and hydraulic properties of the soil used for the reconstruction of the model.
Yep, cool. I look forward to it.
Okay. Unless there is any other question for this part, I think we can proceed to the second part of the presentation.
Okay, I will compress the gallery. And okay. Yes, perfect. Okay, so now we can start with talking about the experimental setup of the two centrifuge tests that I performed in collaboration.
Buonasera. Mi scusi, devo chiedere.
Can you hear me? Can you hear me?
Yes.
Yes.
Okay.
Yes.
Okay, I think there was an interruption. So I will now illustrate the experimental setup of the two centrifuge tests that I performed in the context of the GeoLab Res Fluctis and the technical challenges that we faced. So first of all, we will focus on the 3D geometry of our model, and you can see the scheme on the left side of the slide. So with the black number, I indicated the dimension of the model, while with red numbers, you can see the corresponding prototype, considering a scaling factor of 50, since the acceleration imposed during the test was 50 g. So the material selected for the reconstruction of the embankment is a compacted silty sand, which was taken directly from a floodplain area of Secchia River in Soliera. And it was our stakeholder, AIPO, which is an interregional agency for the safeguard of Po River, which directly provided us with the material. The foundation is a very known material in the literature. So it's a space white kaolin clay that we decided to pre-consolidate under 850 kPa. So on the right-hand side, you can see the grain size distribution of the two materials. So you can see that, for example, the embankment has a very pronounced fraction of sand and a fine fraction which ranges between 7 and 22%. In the table, you can see the main geotechnical indexes and also some mechanical indexes. Here you can look at the hydraulic and retention properties of the embankment, which we understood as a crucial role in the overall behavior, especially for the characteristics of the of the seepage. So the soil water retention curve and the hydraulic conductivity function have been estimated with this high-prop equipment that is tensiometer based. So you can see that even if the air entry value is quite low, around 10 kPa, you can see a gradual passage between the low and the high range of suction. So this is, of course, this gives to the natural mixture great retention properties. The saturated hydraulic conductivity is around 5 to 10 for 10 to the -8 meter per second. Here, in this slide, you can see an animation showing the experimental setup, which includes on the river side a fixed wedge that was used to reduce the water level, the water stored, and to make changes as quick as in the reality. And you can also see 2 LVDTs devoted to the measurement, sitting on the crest and devoted to the measurement of the settlement of the embankment. And on the land side, connected to this adjustable gantry, you can see 3 Raspberry Pi cameras that could be changed in position. On the right side, you can see the overall centrifuge test package. So on the top side, you can see that there is an additional Raspberry Pi camera that was able to look at the section, so this view of the embankment, and also lights, while on the rear side, you can see the data acquisition system, the Raspberry Pis, and an external stem pipe, which I will come back later, that was devoted to control water levels during the test. Regarding the geometry and the instrumentation layout, we can see that the middle section of the embankment was quite extensively instrumented, considering also the dimensions, because we are talking about an embankment which has a height of 15 centimeter and a foundation of 100 millimeter. So the middle section was instrumented with the purpose of recording the time-dependent variation of suction and pore water pressures, and with the LVDT we were able to measure the crest settlement. During the second test, we kept the same experimental setup and model geometry with the addition of a few extra instruments. So, for example, we added at the lower part of the embankment 2 additional tensiometers, and on the crest an additional LVDTs. In this way, we would be able to measure separately the settlements of the land side and the river side part. Okay, now let's go to the core of this webinar. So the technical challenges that we faced during the preparation of the model. So first of all, among these many technical challenges, I have to highlight the need of controlling in a very accurate way water levels, because we needed to be able to impose both steady state and transient seepage conditions. The second need was to, as I said before, to measure the variation of pore water pressure distribution inside the embankment body in order to be able to connect this distribution with the stability in a future analysis. Then we were also worried by the formation of preferential flow channels between the model and the strong box. This is a very key point because if you have preferential flow channels, it is very, very difficult to keep a water level stable and continuous during the test. We also try to impose plane strain conditions and to observe a failure mechanism. So let's start from the hydraulic system. So the hydraulic system was used to control the water level during the test with a combination of 3 main elements. So you can see the already cited styrofoam wedge on the river side, which was used to reduce the stored water volume and to make the changes as fast as in the reality, because we don't have to forget that in the centrifuge test, we have a scaling laws that depends from the square, from the T elevated to 2, considering diffusion processes. Then the system includes also a brass standpipe, which you can see on the right side, which is equipped with 3 holes that work as overflows. So if we wanted to change the water level, we are able to do it in 2 ways. We can, of course, from the slip ring of the main centrifuge, increase the volume of water, so the flow rate coming inside the strong box. But also we can act on these solenoid valves, because you can see from the picture, from the scheme, that these 3 pipes are directly connected to solenoid valve. To better understand this mechanism, since I haven't the possibility to test it in advance in a centrifuge environment, while I was at home with my family, I tried to reconstruct a prototype. So in this animation, you can see a bottle on the left side representing the strong box, and an additional bottle which represented the standpipe. You can see that we had 3 holes as in the proper designed brass standpipe, and you can notice that when these plastic straws are opened, the level inside the bottle remained constant as we are able to keep a steady state condition. But when we apply with this plastic dough, we are simulating the closing of the solenoid valve, the water level tends to increase and to finish inside the strong box. Okay, here you can see the setup that we use for the saturation and calibration of the miniaturized tensiometers. Because another challenge that we had to overcome during the test was the usage of miniaturized tensiometers that were built in-house by the University of Cambridge. So the manufacturing of these instruments was proposed by Professor Jacobs during the International Conference on Physical Modeling in Geotechnics held in 2018 in London. So on his model, we were able to reproduce these low-cost tensiometers and to use them in the centrifuge test. Before the installation inside the embankment, this kind of instrumentation needed to be properly saturated and calibrated. So we use this particular setup that consists in a manifold for which we used an old triaxial cell, in which, with cable glands, tensiometers were sealed, and we could apply at the beginning suction in order to eliminate all the air bubbles, and then we cycled between 0, 100, 200 kPa in order to pressurize them and to saturate the inner chamber between the porous stone and the sensitive instrumentation. Okay, but even if we were able to construct the instruments and the setup for the calibration and saturation, unfortunately, after the initial checks that included evaporation test and the comparison of the trend of suction over time with reference tensiometers, we noticed that even if the trend was really good because they directly reproduce the same values of the reference tensiometers, they cavitated at a very low suction. And of course, it was not possible to use that in a centrifuge environment. So what we needed to do before the installation inside the embankment, we needed to verify all the miniaturized tensiometers and put more epoxy resin. In this way, the chamber between the porous stone and the instrument, the pore pressure transducer, was properly sealed. And now, if you look at the comparison between tensiometer number 1 and tensiometer 1 star in black, you can see that after the cure, the cavitation value was around minus 170. Okay, now I would leave the floor to Mr. Mario Marcolongo that will describe the techniques used for the preparation of the model. So starting from the foundation, and then he will describe also the procedure used for the reconstruction of the embankment. Please, Mario.
Okay, good afternoon. As Alan has just said, I'm going to talk about the technical aspect we faced during the preparation of the two final samples. To prepare the foundation, we mixed the space weight kaolin with the deaerated water to obtain a slurry with a water content around twice the liquid limit. After that, we poured the slurry into the strong box and placed it under the hydraulic press for the consolidation, applying an effective stress about 850 kilopascal. At the end of the consolidation process, we gradually unloaded it, removed both side walls, and trimmed the clay layer to the thickness of 100 millimeters. Later, we mixed the silty sand material with the target water content in order to achieve a suitable shear strength and a low hydraulic conductivity. Then we proceeded to build the model embankment inside the strong box in 4 layers. Using the most temp technique, we constructed the embankment in 4 similar layers. For each layer, the soil was first eventually distributed inside the straw box and then compacted using a rubber-tipped hammer. The hammer was used to strike a load distribution plate until the target compaction was achieved. Between each layer, we installed a very small tensiometer, following the layout shown earlier. The sensitive part of each instrument was first surrounded by a slurry to prevent cavitation. Then, after identifying the exact position using two rules, we carefully placed the instruments, making sure the cables were directly toward the top of the embankment. Afterwards, the embankment was manually shaped using the edge of a trapezoidal acrylic template as a guide and a steel wire as a cutting blade, as it can be seen in the video. Okay. Finally, both the front and rear walls were placed back in the original position. By applying the reconstruction procedure, we obtained a dry unit weight of 16.5 kilonewton per cubic meter in the first test and 16.3 in the second test, with a natural water content of approximately 10%. Both density values are comparable but lower than 17.8, which correspond to the target on the dry branch of the standard Proctor compaction curve at the same water content of 10. This difference is due to the precaution taken to protect the instrumentation, in particular the tensiometer, which, being in prototype phase, were enclosed in fragile casing. Thank you for your attention. I give the floor back to Elena.
Thank you very much. I will activate my microphone and deactivate Mario's one. Okay, so I'm coming back to another crucial aspect that was faced during the preparation of the model. So as I said before, the topic of preventing preferential flow channels is critical during this centrifuge test that includes the usage of water. So to this aim, a very innovative solution was proposed in this test. So between the model and the strong box, we put a very thin layer of a glass clear silicone sheet. And to remove the friction between the two elements, we also sprayed PTFE lubricant. So the main characteristics of these two elements were these three. So the rubber mat was very smooth, and these concurred to the enforcement of plane strain conditions. The material was also very soft, and the grain part of the embankment was solidal to this element. So this contributed to avoid preferential flow channels. And last but not the least, this material is very clear. So as you can see from the images, where me and Professor Vizzani are keeping with our hand the silicone rubber sheet, we could observe very clear failure mechanism. So this lead to the end of the experimental part, so regarding the experimental setup and the technical challenges, and to the second interactive part of the webinar. So have you encountered similar technical challenges during model preparation? And have you ever done some compromises to overcome difficulties in technical modeling? And if so, how they did impact the overall results? Of course, I'm available for any kind of questions.
Thank you, Elena. So who has a question or an answer? Both are nice.
Thank you.
Or even just a comment on whether they think what we did was a good idea.
Exactly.
Did it work?
Yes, he did properly.
Okay, then it was a good idea. But could you explain what is the mechanism? What does this seat that you added do?
So
Why not spray with PTFE the glass window, the perspex window directly?
I did it in a previous centrifuge test, and we noticed that only the PTFE alone was not able to keep the embankment in place. So there was a sort of erosion that concentrated exactly at the interface between the model and the strong box. And grain after grain, it removed the contact between these two elements, while we needed a softer material that was able to include, let's say, the grain in the microstructure. So, and it was compressed because during the preparation of the model, we already put the silicon sheet between these two parts. And so there was a perfect contact.
So what it offers is a bit of flexibility, let's say.
Yes, flexibility,
compressibility
to be, I think it's the right term.
Okay.
And also the help of the PTFE was able to remove the friction, because otherwise a part of the grain could remain attached to the
Did you measure the friction?
No, we don't, unfortunately, but we can show the effect in the video that we were taken during the test. So in the last part of the seminar.
Suffice to say that once you put the PTFE between the silicon and the wall of the centrifuge strongbox, it's very, very slippy. And basically, I think what we're trying to do is prevent suffusion of material on the wall of the strongbox. And so the proof of the pudding for us in the eating is that we didn't see any suffusion at all, and we would have seen it through the window if it had happened.
Yeah. I can also add another observation regarding the usage of this particular material, because now I'm working on internal erosion problems in the context of a European project coordinated by Professor Laura Tonni and Michela Marchi here in Bologna. And we are working also on physical modeling without centrifuge, so at 1G, at the small and medium scale. And I had the possibility to test this solution at the interface between a top cap that closed a container of sand, which is subjected potentially to backward erosion piping. And we notice that this soft layer, there is also an additional element, even softer in that case, but still silicon rubber mat, is able to create a natural contact between the perspex cap and the soil. Mm-hmm. So it works even in this configuration.
I think as well, in the interest of exposing the things that went wrong in the experiment too, Yanis, like you suggested, the first experiment, we used a silicon sheet across the whole model. Yeah. So even the bit where the embankment wasn't present. And what we found was during the test that would flap in the wind of the centrifuge, and we suspect actually impacted the failure mechanism itself. So in the second experiment, we cut the silicon sheet to the exact shape of the embankment, and we didn't have that problem. So even though we thought it was a great idea, it actually probably wasn't the best idea the way we executed it the first time, but the second time was much better.
So how many times did you try to get it right?
Two. Only two.
Okay. But Adam?
Yeah, do we understand you put the silicon between the glass and the sheet, but not between the sheet and the clay? Did you understand that right?
Yeah, exactly. Yeah.
And are you sure that the sheet is so flexible that you will not get if there is shear plane that it will not prevent making a shear plane into the silt?
No, I'm sorry. If I understood well, you said that we haven't used this material on the foundation layer. No, we used even in the foundation layer. So it was shaped along the acrylic template. I can show it. So if you look at this template, okay, this was used both for the reconstruction of the model and to shape the silicone rubber mat.
Yeah, but I'm wondering now if there is a failure in the embankment and in the kaolin clay, then you get quite a difference in movement between the clay particles close together. And
yeah, it's true.
Is that not hampered by these silicon?
Yeah, it's true, but
the sheet, sorry.
Yeah, the sliding surface that we observed were concentrated in the embankment. So the foundation layer was not affected by any movement. Because it was pre-consolidated under 850 kPa. So it was just a base layer, not so rigid as the base of the strong box, but it was not interested by any movement.
Okay.
Does this flexibility affect the out of plane stresses?
I would say it helps instead of affect.
It helps in what sense?
In the sense that since we are working in a closed environment, so we have very small dimension in the centrifuge, it's very difficult to try to simulate a section that would continue for kilometers in the reality. So it is essential to try to recreate some boundaries that does not affect what happens in the middle part.
Okay.
And this was a proposal and it worked. So yes, we will see.
I think there's always a compromise, isn't there? Because you think that by adding the compliant layer, you might affect the generation of out-of-plane stresses along the length of the embankment. But that felt like it was a more acceptable compromise than having suffusion at the outsides and then creating the onset of failure via a funny mechanism that doesn't actually exist in reality. So it's a tricky one, but yeah, that's what we decided to compromise with.
After, if this is exactly the shape of the embankment, after, let's say, the failure mechanism develops and it starts moving, what happens there?
We have some pictures towards the end of the presentation, but since this sheet was very, very thin, it's 0.5 millimeter of thickness, it stayed almost in place. So it didn't move. It was a bit flapping towards the end, but nothing that could interfere. While in the first test, as Sam specified before.
I didn't mean that this moves. I meant that, you know, initially it's touching here.
Yeah.
As soon as it moves out of it, then maybe there is a small gap. I don't know.
No, we couldn't observe any gap between the parts that stayed in place, so not collapsed, and the mat. But we noticed that it was a bit bended in the part in the part where the levy collapsed.
Okay. I see a question. I see Srikanth is raising his hand.
Yeah, hi, thanks. It's really interesting so far, especially that styrofoam block. I think you mentioned you were considering your time scaling with n squared because it's like a diffusive process.
Yeah,
is that
exactly.
still the case if it's partially saturated, where you have kind of maybe advection and infiltration?
This is a very good question. As far as I can say, since I modeled the process through numerical analysis, not in this case, but for previous tests, similar previous tests, it's the scaling laws are quite respected, are respected even if you have an unsaturated contribution. But the process of filtration is slower. So, and this is due to the fact that the material, when it's partially saturated, has a lower permeability than the other one in the correspective in a saturated part.
So, sorry, just to clarify, because it matched well with a sort of large-scale numerical model, the argument is that the process is basically diffusive.
Yeah.
Okay. Interesting. It's always a worry that we would make a model that somehow distorts the scaling, and it's hard to know, right?
I totally agree. The back analysis is very challenging. So, and the fact is that usually this procedure is coupled from an hydraulic and mechanical point of view. So when you do the back analysis of this process, you don't have only to adjust the saturated hydraulic conductivity and the retention properties, but also the compressibility of the model, because these two parts are bonded.
Thank you.
Okay.
Good. Is there any other question at this?
Just a brief one.
Yes.
With the edges, you said you didn't get any diffusion between the model and the edge of the box and the PTFE layer. Do you think there was still any potential for preferential flow that didn't cause diffusion, and it would have changed the saturation profile and or the flow in the across the embankment rather than parallel to the embankment?
Yes, I think it could happen, but in our case, we haven't observed this kind of mechanism. I think that when you observe preferential flow channels, the main concern is not related to the profile, to the retention profile, but the main issue is that in the centrifuge you have a very small volume of water impounded. So when you have a channel that directly connect the river side to the land side, it's not easy to keep the water level constant, and so the test would be compromised.
Yeah, cool. Thank you.
Okay.
Good. If there's no other question, I think we can proceed with the next section.
Okay, and now is Christian Petter's turn. So I would leave the floor to the technician of the Scofield Center.
Hello, everybody. Can you hear me?
Yes, we can.
Oh, good. This is my first introduction to webinars, so excuse me if I'm not the best presenter that you've ever seen. I think from my perspective, I think performing the experiment, as long as the organisation is clear and the information communication is good, then you know, the height of the clay, if there's a plan in place, we know exactly where the instruments are going to go, and we know exactly where what we're going to need for the experiment, whether we can accommodate that with the centrifuge, electrical equipment, so forth, so fifth. Then yeah, I think as long as we haven't got any added extras during the manufacture or getting everything ready for the test, then everything works really well. And having Eleanor and Mario being very hands-on type of people, I think that as in getting their hands dirty and getting involved in the clay and actually, you know, putting their experience in as well to make sure the test worked was really good, because obviously there's quite a small time scale to get everything ready. You know, it starts obviously just scraping the clay, the foundation, and then building it up with the template. there's always going to be a certain few things that may come along, like obviously fitting the sheet that went in between the model and the box, and organising the valves and obviously the wiring and stuff like that. But yeah, I think in the whole everything worked really smoothly, and we achieved what we wanted to achieve with the outcome of the test. So yeah, that's really all I have to say. I think everything worked okay.
Thank you. I think all GeoLab participants will agree with your comments. These were challenges. I mean, in our lab, also our lab was totally new, so we were, let's say, discovering problems also related to the facility while trying to do the tests. So
yeah, I mean, think there was a few unknowns. I mean, with the plastic film, we hadn't used that before. We'd obviously worked with standpipes. We use standpipes quite a lot, and using it with the solenoids to change the height of the water table. But yeah, I mean, you know, apart from you're always going to have a few problems with an experiment, but I think on the main of it that as I said before, if the organisation and the information is clear and the plan is good, then really there should be no problems. So yeah, really good.
It's possibly also worth mentioning at this point too that I think Eleanor really benefited from one of our GeoLab initiatives, which was to make manuals for all of our facilities. So in spite of not being in Cambridge much of the time, although she did come for a number of pre-entry trips, I think having the information on hand for how the lab operated really helped, and it sort of smoothed out the processes once the boots were on the ground in Cambridge. But you know, I think the planning is critical. It's hard enough to get a centrifuge test done when you're local here in Cambridge, with all of the moving parts that these tests entail, and everyone is different. But it's doubly challenging when half of the people involved are, 1,000 or more miles away.
I can totally agree, and also I would like to take this opportunity to say thank you to all the technicians from the Schofield Center from Bologna and from the NERFIS, so the other research center, because all of them helped me in this test. And even if I was abroad, for example, they followed the consolidation of the clay layer while I was away. And I think it was a climate of collaboration between all of them, and even with the other participants of the GeoLab.
Yeah.
So it was a great opportunity for me.
Very happy to hear that. Are there any other comments or questions for this part? Good. Then thank you very much. We can proceed to the next part.
Yes, so we are going to the final stage of the presentation, which includes the main findings and project developments. So I will start this part briefly commenting the results of the two centrifuge tests, and then I will leave the floor to Sam Stanier for the last part regarding stereophotogrammetry that we performed inside the centrifuge, and for the conclusion. Okay, so now let's look at the test results, specifically with reference to test 1. Following the spin up and self-weight equilibrium, the anhydraulic loading was applied in 3 steps. So the first step was in equilibrium with a water level of with a height of 20% of the embankment. Then after reaching the steady state conditions, which was the focus of the first test and the main aim of the first test, we were able to apply a second water level, 50% of the embankment height. This was the hydrometric level reached. Then towards the end of the test, we established for 5 days another 5 days at the prototype scale, but just few seconds at the model scale, we reached a height of 70% of the embankment height, and we observed a failure. In particular, what happened is a progressive saturation of the embankment body, and we can see that as a consequence, decrease in the effective soil shear strength, the land-side slope collapsed. So if we look at the displacement, we can see that the trend of the vertical displacement over time recorded by the LVDT1 sitting on the crest on the land side showed a significant displacement during the spin-up of the model as an effect of the increase of the acceleration, and then minor settlement were recorded during the in-flight consolidation that ended here, and then during the application of the first and second water level. Then we observed a sudden increase during the application of the third water level, and the displacement reached their maximum value in correspondence of T5, so the time instant corresponding to the failure. If we look at the trend of pore water pressure recorded by the 4 tensiometers and 1 PPT, so 1 pore pressure transducers embedded in the middle section of the embankment, at the beginning of the test, they recorded pressures between -2 and -5 kPa. So they highlighted a consistency and homogeneity inside the embankment. Then we observed during the in-flight consolidation a progressive drying of the model, followed by an increase of pore water pressures that was instantaneously reflected by the instrumentation closer to the river side, and then also the other tensiometers positioned in the core of the embankment were influenced by the increase in water level. Of course, the differences in readings is not only function of the water level and position, but also of the retention and hydraulic properties of the soil. So if we want to thoroughly understand what was happening inside the embankment, we need to look to isochrones of pore water pressures. So if we consider, for example, this horizontal plane characterized by the tensiometers position at the middle height of the embankment, we can see that following the first hydraulic load step, the embankment body so the green dashed line, the embankment body resulted still in unsaturated conditions. And even with the second hydraulic load step, only the tensiometer located closer to the river side was reached by the phreatic surface, while as soon as the third hydraulic load step was applied, all these parts of the embankment located almost at 2/3 of the height resulted in saturated conditions. And of course, this triggered the collapse of the landside slope, as we can see from this view of the front camera. Then we performed a second test that, as I said, has almost the same experimental setup, and the main changes was the application of these sequence of peaks and drawdowns. So Following the spin-up and self-weight equilibrium, the water level was raised to 20% of the height of the embankment, and steady-state seepage conditions were attained. Then another water level was applied, equal to 30% of the embankment height. And then the test became a real roller coaster because we observed during the increase of the water level to the first peak, reaching the maximum capacity, we observed both the sliding of the inner and outer surfaces. And at this point, the embankment height, so this 90% of the embankment height, is not the original height of the embankment. So what happened is that the crest lowered, but the soil was still able to retain water. And so we applied these cycles of peaks and drawdown. Then, in correspondence of the last peak, we observed a final triggering of a landslope failure. So if we look at the trend of the displacement, we can clearly see that both the LVDTs located on the crest were able to follow the displacement right until the first failure happened. At that point, we could only rely on the presence of the cameras to describe what was happening regarding displacement. And here we can see that the inner PPTs and tensiometers were in a unsaturated conditions throughout all the spin-up and the self-weight equilibrium stage, and the majority of them continued to stay in these conditions even during the application of the first and second water levels, while during the application of the sequence of floods, high water events, sorry, they were able to increase for their readings. So we can, of course, see even in this case that the instrumentation closer to the riverside is the first that is affected by the application of a water level. And then if we look at the red, at the tensiometer number 1, which is the one closer to the land side, we can notice that as soon as the phreatic surfaces reaches this point, because we can see that we have a clear passage from negative to positive readings, we notice that we observed the failure mechanism, the overall failure mechanism. A special mention goes to the tensiometer located towards the crest. So here we notice that it was not affected by the present by the phreatic surfaces nor by the capillary rise during the test, but at a certain point we notice this peak, and this is related to the fact that following the first sliding and the subsequent decrease in height of the crest, it remained exposed to water. And we can see that it cavitated very fast. But if we look at the value of pore water pressures, we notice that it cavitated at a pressure above minus 200 kPa, so demonstrating the excellent performance and reliability of all the instrumentation. Finally, if we look at the flow rate that we were able to measure during the test through an inlet and outlet point with miniaturized flow meters, we can notice that there is a volume of water that is retained by the embankment body. So thanks to these measurements, it was possible to determine the amount of water stored within the embankment body over a given time interval, demonstrating that the soil is retaining water and gradually becoming saturated. So I would leave now the floor for the part related to front camera view and lateral camera view to Professor Sam Stanier, that will also lead to the conclusion of the seminar.
Thanks. And just a couple more slides to go. So I think I'll just point out the interesting parts here. The keen-eyed will have noticed that when we presented the similar pictures from the first experiment, that you could see the wrinkles in the silicon sheet that we had outside of the boundary of our embankment. Whereas you can see here that all the way from the initiation of the model itself through the initial wetting and then the onset of failure, which you can see in image 3, you can barely see the outline of the silicon sheet. So it did a really good job. It's really quite compliant, stretches really easily. So we don't think it's having a significant influence on the mechanism, although I'll touch on that a little bit later when we look at the views from the 3 cameras that were taking the images we've used for our structure from motion analysis. At the end, it's fair to say that you can see the effect of the membrane moving away from the embankment, but the dam had long since failed by that point. So then moving on, these are views from one of our 3 Raspberry Pi cameras that we positioned looking at the embankment face. And you get a sense from this at how relatively plain strain the mechanism was. It's quite clear that it's not generated on either side of the model. And in fact, we think that the addition of the silicon sheets means that we even take out the difference in the roughness between the Perspex window and the aluminium. You sort of get rid of that asymmetry as well. So that was a really nice aspect. We did see this live. So we've got a nice little web app that takes the images from the cameras and you can scroll through the different cameras and look at the images as they're coming in live. So it gave us some reassurance that all of the hard work in the lab making the experiment was worthwhile on the fly. So moving on, we took the 3 sets of images from the 3 cameras, and then knowing their positions relative to each other, we could input that into some very straightforward to use structure from motion software from Agisoft. And they can then take those images and piece them together and give you this overall failure mechanism. So hopefully you can see from the animation there that the failure really is very close to plane strain indeed. You can go one step further. So if we move on to the next slide, you can take those images and actually get some measurements directly using scaling. So we had some fixed scaling points within the Strongbox environment itself. And this gives you a reasonably, well, what looks quite precise measurement. I'm not sure how accurate it is, but it's certainly precise. And here you can see that we've got a reasonable plane strain mechanism across the box. In fact, you might argue that our silicon membranes have actually almost resisted movement at the periphery, which is the opposite of what you get when you don't have them. When you don't have the membranes, you get preferential drainage through the sides of the model, and you actually get onset of failure at the sides. Now, you might argue we've got slightly earlier onset in the middle, but we think that's preferable. But I think that's a nice point for people to debate at the end of the presentation. So with that, it just leaves me to thank all the people involved. They were a pleasure to work with. And the team at the Schofield Centre as well, who are not acknowledged directly on this slide, very, very committed to making sure that this test was a success. So I'd just like to thank everybody for that. And then finally, I'll move on to the conclusions, which I'll whip through very quickly. So we think the main innovations here, the glass clear silicon sheet has really helped generate a plane strain mechanism. We haven't had suffusion through the sides. We felt that the instrumentation is very invasive. So even those tensiometers, which are very small, are quite large relative to the size of the embankment. And we had long arguments about how many we should have, how big they were relative to the embankment. Is more better, is less better? And the ultimate answer in all of those discussions was, well, it doesn't matter what we do, somebody will criticize it. Somebody would say it would have been nice to have more tensiometers, and somebody else will say it would have been better to have less because then the embankment would have been as impacted by that. So I think that just highlights one of the compromises a physical modeler has to make. The drying case that we've simulated doesn't really represent reality. So we don't have a climatic chamber, but in fact, there isn't one in Europe. So ideally, we'd want to do this kind of experiment in a strong box that has everything in it and also simulates the climate. So maybe that's something for the future. It's certainly something we're thinking about. We've used photogrammetry quite significantly. We think it's added value. It's given us confidence in the plane strain nature of the experiments. So that was a big positive. And Raspberry Pi cameras are so cheap that it's easy to pepper your model with those and get extra insights. In terms of engineering problems, the unsaturated conditions have been shown to be quite important, certainly had a significant influence, and we've been able to identify where the failure has been triggered in relation to the unsaturated condition. But I think just to wrap up, of course, every physical modeler, I think, concludes their experimental campaigns by saying, we need to do more experiments. We need to look at different geometries, different layouts. And of course, if time were endless and budgets were endless, that's exactly what we would do. But with that, I'd just like to thank you for your time and thank you for listening, and open the floor to any further discussion and questions.
Thank you all for a very nice and insightful presentation. Do you have questions for this last part? Adam.
Yeah, so when I compare the numerical results that you showed in the first part with now the measured tensiometer results, then I see quite a lot of difference. So it's of course good to have to be sure that to do more experiments, but if there is no agreement compared with numerical results, then the question is, what's the use? Hey, you see the pore pressures are, you come to -20 or something like that, and in the numerical simulation you come to -60. So that's really it's a factor of 3 difference. So if you have to understand, and also the cause, I have the idea that relatively the experiment is much more permeable than the numerical situation. So yeah, something.
I think it's fair to point out that the tensiometer at what we call the top of our embankment is actually still embedded quite a distance into the embankment itself. So the 60 that you've picked off the top of the embankment in the numerical simulation is actually far higher suction than we would have ever expected to measure with that blue tensiometer in the image there. I'm not sure whether Ellen has done a point-for-point comparison, but from my recollection of the contour plots and the numerical analyses, it was certainly less than 60 that we might have been expecting.
Yeah, exactly. The core of the embankment, as I said before, is around -20 kPa, and it was due to a drying in a controlled environment inside the laboratory. The value of -60 kPa was only measured at the crest of the embankment and along a very thin layer, so which usually desiccated quite fast. So I think it's still.
But to more in general, so it's not the -60, which is really important, but I also the shape of the curve was a bit different. So did you make comparison to the numerical simulations?
I have not reported the numerical simulation for this case, so I have back analyzed these results, but the focus of the seminar was more on technical challenges. So the first analysis that I presented were just a hint to show how much results can change if we consider steady state and transient seepage analysis, and how much the initial conditions can change the overall results. But of course, it's a very interesting observation, and I will take care of these in the back analysis of the 2 centrifuge tests shown. Thank you.
Okay.
Good. Are there any other questions or comments? I see a comment here.
Okay, there is a question in the chat.
Hello, Professor Sam. The difference between the test
Okay.
number 2 with respect to wrinkles developed towards perspex side is it the PTFE lubricant between the perspex and the silicon sheet that made the difference?
No. So the mistake we made in the first experiment was, you imagine we've got the perspex window, which is rectangular, and we started with a rectangular sheet of silicon, but the top surface wasn't connected. So we didn't sort of fix it to the window. So that was fine at 1G, but the minute we span up and wind got behind it, it flapped in the wind. And that's what the wrinkles are that you can see in that image. That's just an immediate sort of momentary snapshot of that flapping of the silicon sheet. And that's why we cut it to the profile of the embankment in the second experiment, and we never saw any further problems like that.
But Sam, if you had, let's say, okay, the part of the sheet that is inside the soil is of course supported by the soil. If you had kind of glued this sheet at the top, would it work also?
I think it would work equally well, but we had 2 rounds of tests in GeoLab. The first one had that problem. We were gambling on which was the better approach for the second one, so we never tried it that way, but it was another approach we discussed. Might have been simpler in some respects, but...
Okay. It was
If I might add something, we fixed in the first test the rubber sheet with the external screws of the strong box. So apparently it was attached properly to the strong box and especially to the perspex. But considering that we are performing tests at 50G in the centrifuge, there is a lot of wind, let's say. So even if at the beginning everything seems good, during the test we could see from the cameras that it was moving.
Okay. Good. Is there any other question or comments? If not, I would like to thank our speakers for this great presentation and all the insights from all the problems and the solutions. It's nice to have solutions to the problems. And I would like to thank also all the participants for being here with us today and for also the questions, the comments. I think it was quite interactive, and I think that anybody who will see this video will really gain a lot. In closing, I would like to remind all of you about our International Conference of Physical Modeling, which will take place in Zurich. We're looking forward to your participation and to welcome you in Zurich. Thank you very much.
Thank you very much. Goodbye.
Thank you again. It was a pleasure.
Thank you. Goodbye.
Cheers. Bye.